next speaker is from the University of Hong Kong, and is Luwei Yang. So Luwei Yang received a Bachelor of Science degree in Electrical Engineering from Xi'an Yangtong University in 2016. He's currently pursuing his PhD degree with the Department of Electrical and Electronic Engineering, University of Hong Kong. His current research interests are in power systems, distributed control, and event-triggered control. Okay, thank you very much, Luwei. I see that you have already shared your screen. So
okay, thanks.
The floor is yours, and good luck with your presentation.
Okay, thanks for your introduction. Hello, everyone. I'm Luwei Yang, and from the University of Hong Kong. Today is a great honor for me to have this opportunity to share my research work with all of you guys. My presentation is related to distributed model predictive control-based frequency regulation for multi-area power systems with energy storage. This shows the outline of my presentation. Firstly, I'll introduce some related backgrounds and motivations. Then I'll provide the main contribution of this work. Finally, I'll conclude my today's talk. Actually, we all know that the key task to operate a stable multi-area power system is to keep the frequency and net inter-area power exchanges close to their nominal values. These two targets are traditionally achieved by automatic generation control, AGC, while making generation follow demand. However, for modern power system with high penetration of renewables, the generation side control paradigm is facing new challenges, as traditional synchronous generators with limited ramping capacities may be inadequate to follow the fast fluctuations of renewables. To tackle this challenge, flexible loads and energy storage devices have attracted considerable attention owing to their advantages such as instantaneous responsiveness and low emissions. Nevertheless, these devices have their own issues when participating in frequency regulation. For example, the operations of flexible loads may have negative impacts on end users, and energy storage devices usually have limited energy capacities. So these devices need to be closely cooperated with the existing synchronous generating units by fully considering their respective characteristics. To achieve this target, various control techniques such as the proportional integral control, robust control, self-adaptive control have been introduced for frequency regulation in the literature. However, these control approaches cannot adequately deal with the multi-variable constraints of a complex power system, such as the ramping limits of generators and the energy capacity limits of storage devices. On the other hand, model predictive control, which determines control actions by solving a constraint optimization problem over a receding finite time horizon, can be a potential solution for this drawback, owing to its capability of handling hard constraints in multi-variable systems. Due to its advantages, the MPC-based frequency control has attracted increasing attention, and numerous centralized corresponding controllers have been developed. But centralized approaches may cause a heavy communication burden for the control center and are vulnerable to single points of failure. So this motivates us to propose a distributed MPC-based frequency control algorithm, which only relies on local information and information sharing between separate connected buses. Now we consider a connected power transmission network with N buses and tau control areas. We partition all buses into NG generator buses and NL load buses, and assume that each load bus has a controllable load or an energy storage device, and we allow the situation that a single bus can have both or does not have any one of these two devices. To describe the dynamics of the power network, we adopt the nonlinear structure presuming model as shown in equation 1. Here, for each bus, we denote omega I, PBI as the local frequency deviation from its nominal value and net power flow out of bus I respectively. For each generator bus, PMI, PGI are the mechanical power input and load reference set point respectively. For each load bus, we denote RI as the local net demand equal to non-dispatchable load minus renewable generation and represents the external disturbance. PLI is the power consumed by the controllable load. PCI, PDI are the charging and discharging powers of the energy storage device, respectively, and EI is the corresponding stored energy level. It should be noted that for buses that have no controllable loads, we simply set PLI equal to 0. And for buses without energy storage devices, we simultaneously set EI, PCI, PDI equal to 0 at the same time. Based on these notations, equation 1b describes the frequency dynamics of generator buses, and 1c, 1d are the corresponding turbine governor dynamics. Further, equation 1e describes the power balance of load buses, and 1f denotes the energy dynamics of storage devices. Finally, equation 1g is the power flow equation, with Ni here being the set of buses that are physically connected with bus I through transmission lines. Now we can specify the control target of this work. We aim to develop a distributed model predictive control-based frequency control algorithm for system 1, which can regulate the system frequency and net inter-area power exchanges close to their nominal values by optimally coordinating the power produced by synchronous generators, power drawn by controllable loads, and power charged or discharged by energy storage devices with the operational constraints of the system satisfied. To achieve this target, we firstly rewrite the system model in the state space representations, where the load reference set points are control inputs for generator buses, and power consumed by controllable load, as well as power charged, discharged by energy storage devices are control inputs for load buses. Then at each sampling instant, with TO being the constant sampling period, we use the linear discrete time model 3 to predict the future behaviors of this system 2 over this receding prediction window, where NP denotes the total prediction step, and the K here is the discrete time prediction step index. To derive model 3, we linearize system 2 at each sampling instant, and discretize the obtained linearized model with the sampling period 2. So the system matrices of 3 are updated at each sampling time, and all delta variables are the deviations at step K from their current values at the corresponding sampling instant. In what follows, we will simply denote these system matrices by putting the time index H into their subscripts for notation of gravity. Based on the prediction from 3, we formulate our control target as the MPC problem 4. At each sampling instant, the MPC problem is solved over the prediction window, and only the solution to the first time slot is used to dispatch the controllable units and keeps unchanged within the current time slot. This process is repeated for the next time step by using the latest forecast net demand profiles. In problem 4, constraint 4A serves as the predictor of the system future behaviors. Constraints 4B, 4C are to make bus frequencies stay within their admissible ranges. 4D, 4E describe the constraints on the power outputs and ramping rates of generators. The power consumptions of controllable loads are limited by 4F, and the charging discharging powers of energy storage devices are respectively bounded by 4G, 4H. Constraint 4I denotes the energy capacity limits of storage devices. Finally, constraint 4J uses delta PTSK to predict the night time power deviation of the control area S at step K from its current value at the sampling instant. For the objective function, we adopt the quadratic penalty terms for mismatches of bus frequencies and net inter-area power exchanges from their nominal values. Further, we use the standard quadratic generation cost and use their disutility for each generating unit and controllable load respectively. The linear cost function of both charging and discharging powers is adopted for each energy storage device. So the objective function of the MPC problem aims to minimize the total penalty of bus frequency and net inter-area power flow deviations from their nominal values. and also the total operation cost and user disutility of all controllable units across the whole prediction window. It should be noted that since our considered storage cost function is monotonically increasing according to this reference, it can prevent the charging and discharging powers from being simultaneously non-zero, which guarantees that energy storage devices can only operate either in the charge or discharge mode at any time. To facilitate the later design of a distributed solution algorithm, we rewrite the formulated MPC problem in this matrix form, where the Captain omic are three feasible sets of decision variables, delta x, y, u. Since the MPC problem is convex, its optimality conditions can be obtained by using the well-known KKT conditions, which are summarized in this slide. For these optimality conditions, 6a to 6c relate to the decision variables delta x, y, u. 6d relates to the net inter-area power flows, and 6e, 6f correspond to the generator's ramping rates. Here we denote P as Ksay as the projection of a vector Ksay onto a closed convex set, Captain S, and denote C as Ksay as the corresponding normal column. So now we are in position to solve the MPC problem in a distributed way. We assign each control area a connected communication network whose topology contains all the links of the area in the physical transmission power network. Furthermore, we connect the communication networks of physically interconnected control areas by adding links with the same ends as the corresponding town lines. Suppose that any two directly separate connected buses in the entire communication network can share information with each other. Then at each sampling instant, we ran the design dynamic system 7 at each bus for all time slots within the prediction window in parallel to solve the formulated MPC problem. In fact, we have shown in the PSCC paper that when the design algorithm converges, the steady state values of these four terms are actually an optimal solution of the MPC problem. Here, x, y, u, v are four variables defined in the design dynamic system. Now I'll briefly explain the design rationale of this algorithm in the following several slides and provide again the feasibility and optimality conditions of the MPC problem with blue boxes for your reference. Firstly, setting the derivatives of alpha, beta as 0 at the equilibrium point gives equation 8. If you compare equation 8 with the conditions at its right-hand side, you can find that the prediction constraint is satisfied by introducing the alpha-beta dynamics. Secondly, letting the derivatives of lambda mu equal to 0 gives equation 9. According to this lemma from the reference published in IEEE transactions on automatic control, equation 9 is equivalent to 10, which implies that the feasibility and optimality conditions related to the ramping rates of generators are satisfied by introducing the lambda mu dynamics. Thirdly, the projection operators here are used to make decision variables stay within their corresponding feasible sets all the time. Fourthly, setting the derivatives of these three variables equal to 0 gives equations 11, based on which we can get equation 12 by conducting some routine calculations. Then by combining the facts 12b, 12c, and recalling the definition of PTSK, we have the feasibility and optimality conditions related to the net inter-area time power flows are satisfied by introducing these three dynamics. Finally, by using the basic properties of the projection operator and a normal column given in this book, we can easily get the optimality conditions related to the decision variables are satisfied by introducing these three dynamics. Here it is worth pointing out that N-itude denotes the index side of buses that are separate connected with bus I and located in the same control area. So the design dynamic system only depends on local information at each bus. Some information broadcast from all of its neighbors in the intercommunication network, and some other information only from the several connected buses in the same control area. Therefore, the designed projection-based algorithm can solve the formulated MPC problem in a fully distributed way. In this presentation, I only give some brief ideas about the design rationale of the design dynamic system. For more details, please refer to the full paper. In this work, we test the effectiveness of the proposed algorithm on an 8-bus power system with 2 control areas. The time-varying net demand disturbances shown in figure 2 are applied to load buses, and for brevity, we assume that no prediction errors exist. Then the state responses of the area-wise frequency and net inter-area power exchange deviations from their nominal values are shown in figure 3 and 4 respectively, where the solid lines correspond to the MPC-based method and the dashed lines correspond to the traditional ATC. Here, the frequency of each control area is synthesized by adopting the concept of center of inertia. It can be observed that the frequency deviations can be constrained within a narrow range by the designed MPC-based frequency controller, and a better control performance can also be achieved. More comprehensive simulation results with respect to how the operational constraints of the MPC problem are satisfied are presented in the full paper, but not included in this presentation due to the time limitations. In a summary, we have studied the frequency regulation problem of multi-area power systems by proposing a distributed model-predictive control algorithm that can regulate the system frequency and net timeline power flows between interconnected control areas. The frequency regulation task has been firstly formulated as a constrained MPC problem, and then a distributed projection-based algorithm has been proposed to solve the resulting optimization problem. That's all for today's presentation. Thank you.
Okay. Thank you, Luwei. Thank you for the very nice presentation.
Yes.
So we have a few questions from the audience that I'm going to read you so that you can answer them. So Zhao Yuan asks, first, how do you select the parameters of the penalty coefficients in your cost function? And at the same time is also asking if you have verified the KKT conditions in your linearization and discretizations. Because if the regularity conditions are not satisfied, the KKT conditions might not be sufficient for optimality.
Okay, yeah, that's good questions. I think as for the first question, I think in my work, I only to test the effectiveness of the proposed method, I only select a set of parameters instead of testing the method by using different types of parameters. How to select the parameters? I think just for me, I just use I think in this work, I do not consider how to select the parameters. I just use the parameters from some reference. And I also give the reference in the full paper. So if you are interested, you can refer to the paper. As for the second problem, I think how is the accuracy of the proposed linearization and discretization? Oh, I think if we use small time resolution for the linearization and discretization, I think the accuracy can be guaranteed. For the optimality of the KKT conditions, no, I think in my problem, it's actually a general convex problem. So the optimality conditions can be exactly determined by the KKT conditions. I think the KKT conditions is already sufficient for the optimality. I think that's my opinion.
All right, okay, thank you. So we'll take another question from the audience. There is a question from Joachim Bjork, and is asking whether closed loop stability can be guaranteed in the distributed MPC.
Yes, the answer is yes. Actually, we have proved the convergence of our proposed distributed solution algorithm for the MPC problem. And then if you select how to say, the proper parameters for MPC problem, I think the closed loop stability can be also guaranteed accordingly.
Okay, all right. Okay, I think there are a few other questions in the questions and answer panels. You can, I think, type your answer maybe directly there in the panel, replying to the single questions if you want. We are done with the time, so I would thank you once more for your nice presentation, and we move to the next presenter. Thank you, Luwei.